Hello everyone, my name is Danyang Liu, and this is my journal club presentation for our group, and this is the paper I'm going to talk about. And there are two reasons why I choose this paper. The first one is because this work used STM-based ESR technique to measure the magnetic dipole and dipole interaction with atomic precision. And there are a lot of experimental details to talk about. And this technique is also what we are going to use in our future experiment. So I think it's valuable to learn and discuss about all the details in this experiment. The second reason is this work provided a new method to atomic scale remote sensing and structural imaging by the achieved high-resolution iron sensor, which I found is very fancy and interesting. So based on these two reasons, I would like to present this paper to all of you. Firstly, I would like to give you a little bit of the background. And in the traditional magnetic resonance experiment, it is typically required an ensemble of 10 to 7 to 10 to 10 spins. So in order to detect individual spins, there are a lot of techniques which have been used so far, like NV centers and the spins in quantum dots, or single molecular magnets in break junctions. And so far, the achieved resolution of the controlled positioning of the spin center is about 10 nanometers. So the atomic scale control, which is less than 1 nanometer, still remains a highly challenging goal. And now let's have a look at the experimental setup as it is shown on the picture. The author here, they deposited individual atoms. Here is iron atom and cobalt atom onto a bilayer of MgO, magnesium oxide. And the MgO was grown on a silver substrate. The silver substrate was prepared by repeated argon sputtering and annealing cycles at about 450 degrees, and the magnesium oxide was obtained by evaporating magnesium for several minutes in the oxygen atmosphere at about 320 degrees. And in order to evaporate iron and cobalt atoms, they evaporated at about 10 Kelvin using electron beam evaporation. And the whole STM setup was operated at temperature about 0.6 Kelvin, and also they applied an external magnetic field. The out-of-plane magnetic field is about 0.15 to 0.21 Tesla. Now let's figure out more details about the experimental protocol for the electron spin resonance experiment, ESR experiment. And from the picture here, we can see there is a spin polarized STM tip over an individual atom. And also there is a gigahertz frequency voltage, VRF, was applied between the tip and the sample, in addition to the DC bias voltage, VDC. And the RF voltage created a time-dependent electric field between the tip and the sample. When the frequency of the RF voltage is resonant with the Zeeman splitting, the field drives the spin transition between the two lowest states. Here is the state 1 and state 0, between these two states, and in this way depopulating the ground states from its thermal equilibrium. And this change of density of states will be detected with the spin polarized STM tip by the tunneling magnetoresistance. And this DC voltage will be used to measure the tunneling magnetoresistance of the tunneling junction with the STM tip. And in the magnetoresistance junction will result in a tunneling current that dependent on the relative population of the states. In this way, when the system reaches the tunneling frequency of the spin resonance, it will show immediately and obviously as a signal because of the additional tunneling current. This is the experimental protocol of the electron spin resonance experiment, ESR experiment. And also there would be a question why we put MgO between the silver substrate and the atoms. And it is because, firstly, the MgO film will reduce the scattering of the atoms between the substrate silver electrons to the individual atoms, and which will lead to a longer spin relaxation time, which is good for our experiment. And the other reason is that when we put individual atoms onto MgO, and the iron atom or cobalt atom, they prefer to absorb onto the oxygen of the MgO, which will create an easy access magnetic anisotropy for our individual atoms. And here for iron atoms, the easy axis is out of plane and perpendicular to the surface plane. And also because of the 4 magnesium atom around the iron atom, it will create a 4-4 symmetry, which is good for the magnetic anisotropy. Okay, equipped with the previous knowledge, now we can come to measure the magnetic interaction between iron atoms. From previous studies about the ESR of single iron atoms, when there is no external magnetic field, the ground state has 2-fold degeneracy. And when we apply the magnetic field, because of the Zeeman splitting, the 2 lowest states, the ground states, will split into 2 energy levels. And when the frequency of our continuous RF voltage is resonant with the Zeeman splitting of the atom, the field will drive the spin flip between the 2 states up and down, which will result in the peak shown on the ESR spectrum. And after verifying the system on a single iron atom, now the author can continue to focus on the magnetic interaction between 2 iron atoms. They position the STM tip above one of the iron atoms, which they called the sensor atom, in a pair and measure its signal. Since there are also 2 states of the target atom, which is the other atom in the pair, and spin up and spin down. So they obtain the ESR spectrum like this. From this figure, we can see the ESR signal has 2 spectral features, which corresponds to 2 oppositely oriented magnetic states, which is spin up and spin down of the target atom. And why the energy level from low to high orders in this way, in my understanding, probably is because for single iron atom, spin up perpendicular to the surface is the lowest energy state, while for a pair of iron atoms in the range of dipolar interaction, I think the anti-parallel alignment is favored by the dipolar interaction. So in this way, the ESR frequency difference delta F gives the magnetic interaction energy, which is calculated in this equation, which is approximated in the most ideal model. When the distance is greater than 1 nanometer, we can see from this picture, it fits excellently with the exponent alpha equals -3. However, when the distance d is lower than 1 nanometer, the coupling deviates remarkably from a pure dipole-dipole interaction, which indicates that it is influenced by an additional interaction, such as exchange coupling. And moreover, based on the value of the dipole interaction energy, we can also calculate the magnetic moment of single iron atom, and this creates a new way to measure the magnetic moment of individual atoms with very high precision. And also we can find it here that the interaction energy only dependent on both magnetic moment of these two individual atoms, and also dependent on the distance between these two atoms. And it is not dependent on the detailed structure of the tip or the environment temperature and the external magnetic field, which is quite important and will be further proved in the further experiment. And from these control experiments for the distance dependence ESR splitting, we can find the ESR splitting delta F does not depend on the parameters such as temperature and magnetic field for the ranges measured. Also, it is observed there's no dependence of delta F on the crystal direction of the plane or the substrate orientation, which is investigated by employing various crystal orientations. And most importantly, the STM tip termination does not affect the ESR splitting as well, which can be seen from the figure C and figure D. Even though we can see from here the absolute frequency F is affected strongly by the choice of the tip apex, and the sign of the ESR signal corresponds to where the Z components of the tip spin polarization follows the direction of the external magnetic field, which is the common case, and will reflect as a dip in the ESR signal. Or in some other cases, which is not that common, the spin polarization is opposite to the external magnetic field Z component. Then it will create a peak in the ESR signal. So we can see here the sign of the ESR signal is also affected by the tip apex. But the dipole-dipole interaction, the delta F, is not affected by any of those parameters. And what more information we can get from this ESR splitting figure is about the ESR signal height analysis. We found that the higher frequency ESR peak has a smaller amplitude than the lower frequency one. So the authors studied the relative amplitude, either height or the area of those two ESR peaks as a function of the sample temperature from 0.6 Kelvin to 1.6 Kelvin. And the author found the ratio of the two ESR peaks heights, which is also the ratio of the thermal population of spin down to spin up, agree well with the Boltzmann factor, which is 0.4 at temperature 1.2 Kelvin, as it is shown in the figure B. According to this fit, we can also calculate delta ET, which equals 22 gigahertz. And this value is actually the ESR frequency of the target iron atom. And in order to verify it, the author also put the spin polarized tip above the target atom and to measure the ESR frequency with the spin polarized tip and get the measured value to be 24.8 gigahertz. We seem to have a big difference between 22 gigahertz to 24.8 gigahertz by two different methods. But we have to remember the presence of the spin polarized tip over an atom will create the changes of about 1.5 gigahertz. So in this way, we can see even though the absolute ESR frequency F is affected strongly by the structure of the tip is about 1.5 gigahertz, but the measured dipole-dipole interaction, delta F, is still dependent of such details, which again proves the conclusion above. And here I also would like to note that because the spin relaxation time of the iron target atom was measured by pump probe spectroscopy to be about 100 milliseconds, which is much faster than the data point averaging time in the ESR spectrum, which is about 1 second. Therefore, our ESR spectrum here on the iron sensor statistically samples the thermal population of the target iron spin at each data point. In this slide, I would like to present the calculation on the magnetic dipole-dipole energy because this equation shows the most general case that how we calculate the magnetic dipole-dipole energy between two magnetic moments. And from the figure A, we can see this is the most ideal case where the two magnetic moments are aligned with a z-axis and are perpendicular to the surface. This model applies for identical atom spaces with zero in-plane field. And for the figure B, we can see this is the most general case of the magnetic dipole-dipole geometry considered here. And figure C, we can see it is a special case of figure B, representing the case of identical atoms, iron and iron, but it has a canting of the magnetic moment due to the strong in-plane field Bx. And the figure D is also a special case of the figure B, showing the different effective atom heights above the surface due to non-identical atom types. So figure A, we can calculate it in the equation that I mentioned above. It's the most ideal equation approximately in this way. And if we want to consider the error about the most general cases, then we have to calculate the error calculation in this way. The experiment we introduced above gave us the accurate determination of the iron atom magnetic moments, which enables us to use this iron atom as a sensor for measuring the magnetic moment of other target atoms. So the author creates such a 5 iron atom structure, firstly in a broken symmetry. And so in the following, the author used a single sensor atom to prove such symmetry of the dipolar field from several target atoms. Firstly, we placed the 5th atom, which is a sensor, off-center in the square to create different distance to each target atoms. Because there are 4 target atoms at each corner, so for each atom, we have 2 states, spin up and spin down. So there are 2 to 4 equals 16 possible states for the target atoms. And each yields a distinct ESR frequency in the sensor atom, which is in the middle. These ESR frequency signals are shown as the vertical lines in the right figure. And this spectrum shows a dominant peak, which is the gray line. I think it is due to the target atoms. Mostly they prefer to residing in their ground states. So the gray line means all the target atoms in their magnetic ground states. So according to the Boltzmann distribution, it has the biggest amplitude. And the pink lines represents one of the 4 target atoms is in their excited states, which has the second amplitude individually. And all these additional ESR lines with less intensity shows when 2 or more of the corner atoms are in the excited states. And because of this broken symmetry in this system, so we can see there are no ESR transitions degenerate. Here in this slide, the author created a four-fold symmetry system by putting the sensor atom in the exact center with the same distance to each corner atoms. This four-fold symmetry leads to the degeneracy of the excited states, as it is shown in the figure, is 14641 degeneracy. For example, the pink lines in the broken symmetry, there are 4 separated pink lines, but now those 4 pink lines are all generated at delta F equals about 0.2 gigahertz. And also for those green lines, it represents there are 2 corner atoms in their excited states, so it has the degeneracy of 6. Also, we can see it clearly that there are 2 temperature spectrum. One is 0.6 Kelvin and one is measured at 1.2 Kelvin. We can see it is clear that when the temperature increases from 0.6 Kelvin to 1.2 Kelvin, the population of the excited states also increases. It transfers the spectrum weight to higher frequency peaks, which corresponds to more of the corner atoms being in their excited states. So furthermore, this spin structure can also be used as a local thermometer by fitting the ESR spectrum to the dipole-dipole interaction. And here now, the author did something looks fancy. They employed tertiarization, which is the geometrical technique used for macroscopic location by the GPS. The author creates such a Nano GPS by spin-resonant iron atoms. And the position of the unknown atoms based on this technique will fall at the intersection of the circles of the unknown radius around its sensor. So as it is shown in figure A, we treat the middle iron atom as the unknown spin center. And now we are going to sense its location and magnetic moment purely from the ESR spectrum of the 3 iron sensor atoms. But as a slight complication, the ESR signal we get from each sensor atom is convolved by the effect of other nearby sensor atoms, as it is shown in the figure B. So now the author removed this effect on the spectrum by numerical deconvolution. So the figure C shows derived spectra due only to the interaction of the middle target atoms with each individual sensor atom in return. And in order to calculate the location and the magnetic moment of the unknown atoms, there are actually 3 unknown parameters: the x and y coordinates and the magnetic moment of the iron in the middle. The author provided the equation as it is shown in this slide. However, we have to get 3 sets of the parameter in order to calculate the 3 unknown parameters. So we get 3 sets of the parameters from the 3 sensors ESR splitting. In this way, we put on these parameters into the equation, then we can calculate the x unknown, y unknown, and the magnetic moment of the target atom. And also the author provided here the resolution of the location is better than 0.1 nanometer for the location. And for the magnetic moment, the resolution is better than 0.1 millibor for the calculated magnetic moment in this Nano GPS technique. And furthermore, we can see from figure A that the author explored how to detect 2 unknown spins simultaneously with these 3 sensor iron atoms. And from figure B to figure D, we can see for each sensor, it exhibits two sets of ESR splitting. Even though some of the ESR splitting, as shown in sensor 1, it's difficult to extract precisely because of the significant influence of the neighboring signal. But this still presents us a good resolution of how to position the more than one spins simultaneously with the Nano GPS by spin-resonant iron atoms. Okay, this is all about my presentation, and I hope you enjoy it. If you have any questions, please feel free to comment below or to contact me. And thank you for your attention.